Hi everybody, and welcome back to our vlog series. My name is Alexander Stremitzer, and I'm the Professor for Law, Economics and Business at ETH Zurich. When deploying machine learning algorithms for high-stake decisions, for instance court decisions, we want to ensure that these decisions are fair and equitable. Now, a huge literature has developed to basically diagnose and fix these biases in machine learning algorithms. But this literature has not explicitly taken into account the fact that usually we don't delegate decisions to machines, but machines merely assist humans who retain the ultimate decision-making power. In other words, there's always a human in the loop. Now, it might be that this is irrelevant for designing algorithms, that the same properties that you would like to have in a situation where the algorithm makes the decision would apply also to the situation where there's a human in the loop. But who knows? Talia Gillis is a professor of law at Columbia Law School and a lawyer and economist by training, and she gave a lecture at ETH yesterday where she presented a mathematical model that shows the possibility that there are dramatic effects of taking into account this human-AI interaction for the architecture of a desirable algorithm. Talia, welcome to the CLE. Can you tell us a little bit about yourself and how you became interested in this topic?
So as a graduate student in the economics department and the law school, I was very interested in kind of consumer finance and the regulation of consumer finance. And one of the things I noticed was a significant transformation that was taking place in the world of consumer credit, in which decisions about credit allocation, about whether to grant a loan and on what terms, was increasingly relying on more and more data and alternative data, what kind of is often known as big data, as well as kind of advanced statistical methods like machine learning. And I was very interested in the impact this might have on households and the allocation of credit and how we might regulate consumer finance and consumer credit markets. At the same time, at the economics department, machine learning was increasingly being a tool incorporated into kind of the economist toolkit. And there was a lot of reckoning with this question of both what are the implications of AI for economic outcomes, but also how do we think about machine learning as a tool, as a statistical tool, different from other classical econometric methods. And the kind of combination between the two really motivated me to think more about what it would mean to use these different statistical methods and these different alternative data in the allocation of credit. And kind of in economics, you're really pushed to think about concrete outcomes rather than just kind of properties of algorithms in isolation. And on the law side, there was a lot of focus on thinking through how regulation kind of impacts the real world, not just kind of regulation on books, but actually regulation in practice in the real world. And so together with Jann Spiess, who was with me in graduate school, and Bryce McLaughlin, we got together to think about how there's this real dissonance in a way between much of the algorithmic fairness literature that talks about the properties of an algorithm kind of in isolation to the way AI is deployed in the real world that often involves a human decision maker and human discretion.
Mm-hmm. So what is the main outcome of your paper? What is the main result of your paper? You do a mathematical model and you try to take into account all these details. So what do you find?
Yeah, so the key insight is that the optimal design of an algorithm depends entirely on how exactly an algorithmic prediction is going to be implemented in practice. And if we think of these two models of decision-making, one in which we call automation, in which an algorithmic prediction is directly translated into a decision, versus a situation in which there's a human who has decision authority, who uses the algorithmic prediction as a signal and then makes a decision, well, that's going to have implications for the optimal design of an algorithm. And what we do in our paper to demonstrate how kind of meaningful it is what decision world we're in is by focusing on this kind of fairness metric. How would we build an algorithm that leads to fair outcomes? And it turns out that how we design an algorithm to lead to fair outcomes very much depends on which world we're in terms of decision making. So in an automation context, you might design an algorithm, for example, to exclude a protected characteristic to make a prediction and make that decision fairer. But in a world in which kind of there's a human decision maker making a decision, then it depends very much on that human's decision maker's priors. So for example, if a human decision maker has what we call kind of an inaccurate statistical bias, in the sense that they believe that controlling for all covariates, outcomes are going to look different for a protected group, for example, for men and women, then maybe we would want to include a protected characteristic in the algorithm provided to that human decision maker to correct the bias. So what's important is when we think through these properties of fairness and how they relate to the optimal design of the algorithm, we have to think of the actual implementation of the decision.
Could you please give us a specific example how this would play out in practice?
Yeah, so let's assume I'm applying for a loan. I go to a bank and I provide various information about myself. I provide the bank with information about my income, about my wealth, about my debt to income ratio, so kind of previous loans that I've received. And say the bank kind of uses that data to produce some prediction of creditworthiness. Now, in a world of automation, that information may be used by a machine learning algorithm to provide some prediction of creditworthiness, and that might directly translate into whether I get a loan and at what terms. So we will call that automation because there's no human involved in that decision. It's kind of based on my characteristics. But let's assume there's a loan officer that I meet with at the bank, and the loan officer receives that prediction of creditworthiness, but also has some discretion about deciding whether in fact I get that loan and at what terms. So that would be a world of assistance in which there's a signal used by the human loan officer with discretion. Now, we may ask ourselves, what kind of design should there be for that algorithm that's producing that prediction to produce fair incomes, let's say, for male and female borrowers? So in a world of automation in which that decision is directly, the prediction is directly translated into a loan decision, we might say, well, we don't want that algorithm to include my gender, because including my gender may mean that the algorithm can provide different decisions for men and women controlling for all their other characteristics. But when we think about the decision making, which is a loan officer who's receiving that signal and then has discretion, then so much will depend on what that loan officer's beliefs are with respect to me as a borrower. So for example, if that loan officer thinks that women are less creditworthy than men controlling for all those other characteristics, and they want in fact to provide a loan only to borrowers they believe are truly creditworthy, then if they get a signal from the algorithm that they know has excluded my gender, they might say to themselves, well, here's an algorithm that has a prediction of creditworthiness, but I know something that algorithm doesn't know. I know the borrower's gender, they know my gender. And so the decision ultimately might reflect a combination of their beliefs about the effect of gender on creditworthiness and that signal. But let's assume they're wrong about that creditworthiness, that women are less creditworthy than men. Then if we had an algorithm that used gender as well in creating this prediction of creditworthiness, and the loan officer knew that that prediction of creditworthiness included my gender, then that would mean that actually they would be more likely to adopt that recommendation and not treat men and women different. So if we really care about outcomes in terms of, am I as a borrower getting different terms than kind of male borrowers, if that's what we truly care about, that fairness metric, then actually the way we design the algorithm to achieve that fair outcome very much will change depending on the beliefs of that loan officer.
This is really fascinating. Now, what you showed in your paper was a possibility result. It's a mathematical model. It makes certain assumptions about human behavior, about the environment, and you show that it can arise that there is this strong effect of this human-AI interaction on the design of the optimal algorithm. Now, what are the next steps that you're planning to convince us that this is also a practically relevant scenario?
Yeah, of course, that's very important because, as you mentioned, the point of the paper is not to say that this will always be true or that we should always include a protected characteristic, but rather that this might be true in certain cases. And so our next step is we want to test the predictions of our model in an experiment. And specifically, we want an experiment in which people have some kind of inaccurate statistical bias, meaning they believe that, for example, their gender differences controlling for all other covariates. And we want to see the impact of providing, let's say, a decision maker with an algorithm or a prediction that includes or doesn't include the protected characteristic of gender. So the context in which we're thinking of studying this is with respect to either IQ tests or math tests, in which, based on prior research, we think there's an inaccurate statistical bias in the sense that people believe the gender disparities are larger than they are when it comes to answering math questions and IQ questions. And so at the first stage, we're going to collect these test results of participants on these tests. And at the second stage, we're going to ask evaluators to guess the scores of various participants, providing those evaluators with various characteristics of the participants. And then we'll provide an assistant to each of the evaluators. And this assistant varies based on what characteristic it averages results based on. So an evaluator will be told, participant 525, she is a graduate student with an income of above $100,000. We know that people with income above $100,000, their average score was X. What do you think her score was? For other participants, we'll say, we know that the average of women with $100,000 is X. And the comparison between the guesses we get for those two treatments, one that includes the conditional average with gender and one that shows the conditional average without gender, will tell us whether providing that additional information or that algorithm, the conditional average with a protected characteristic, actually led to the guesses or the evaluations to be closer for men and women.
Mm-hmm. So if this experiments can confirm your main hypothesis, what do you think is the main implication for regulation? Because you said you were originally motivated by informing policymakers on how to regulate algorithmic decision makers. So how would that have an effect on how the Europeans, but also the US, should think about regulating these algorithms?
Yeah, so the main motivation would be to put a lot more thought on how we should regulate or what requirements we should lay down for algorithms in a world of assistance, and not just assume a world of automation in which algorithms are directly translated into decisions. So in many critical domains, we know that we have a model of assistance. So very often algorithms employed in the context of employment or in credit, in judicial bail decisions, in all those examples, we very often have a human decision maker. And yet the regulation in a way overlooks that aspect of assistance. And perhaps more striking, when we think of kind of emerging approaches to the regulation of AI, for example, as we see in the European Union proposal for the regulation of AI that was circulated last year in April, it puts a huge emphasis on requiring actually human discretion and human decision-making in the process. In a way, the emerging regulation approach is to say we don't want to be in a world of automation, we want to be in a world of assistance. But those same pieces of regulation that impose this decision-making structure of assistance also create so many regulatory requirements that overlook that structure and kind of treat the algorithm as the kind of be-all and end-all of the decision. So for example, requirements to audit an algorithm, to oversee an algorithm, to check the fairness properties of algorithm, all kind of different requirements that are emerging in the world of regulation of AI. They all kind of require to evaluate those properties just on the algorithm itself, even though we know that the algorithm is going to be used as a signal for the human decision maker. So the most important policy implication here is as we're drafting our requirements for the regulation of AI, we need to be sensitive to the fact that in the real world, we're seeing this kind of implementation through assistance. And so our requirements in terms of what needs to be tested and what safeguards we have actually have to look at the ultimate decisions and not treat the algorithm in isolation, given the decision-making structure.
Well, it seems that the main message is that creating consistent regulation is actually less straightforward than one would think. So thank you very much for these fascinating insights and sharing this with our viewers. And to you at home, thank you very much. See you next time.